I'm going to talk today about C++ and hardware. This is a talk I gave for the first time a couple months ago at CPPCon. I've since added a few minor bug fixes and improvements today. So just one slide about myself and what I actually do. I work at ROLI, which is a music technology company in London. We make essentially software and hardware to produce and perform music. And we also make Juice, which is an open source cross-platform application framework, which is written in C++. It runs on Windows, Mac, Linux, iOS, Android. It can be used for writing all kinds of apps. It's very popular for audio and music production software. A couple hundred companies use it. So this is sort of my background. And audio algorithms, or music audio algorithms, are a lot about number crunching, right? So we have to produce something like 44,000 audio samples per second, and we have to send this to the sound card. So there are certain similarities to things like games, finance, scientific computing, and other low latency applications. But also in audio and music, we have a real-time environment. So this is a very fascinating problem in itself. If you're interested more in about how that actually works, you can check out my CPPCon talk from last year, which is called C++ in the audio industry, where I talk a little bit more about that kind of stuff. But the bottom line basically is we use C++ and we care about performance, as I imagine many of you do as well. One thing that I found there is, if you do C++, you can learn C++ and know C++ really well, and you can know data structures and algorithms very well. And then, you know that quicksort is going to be faster than bubble sort, and you know that if you want to remove elements from a vector, then probably the erase-remove idiom was going to perform better than individually removing elements from a vector and then shifting it, so it's going to shift every time. So, a lot of performance things can be improved by using the appropriate data structure and the appropriate C++ techniques. But there's also one other thing is that no matter how good you know C++ and no matter how good you know all this stuff, sometimes that's just not enough. And sometimes if you want your code to have optimal performance, you actually need to know something about your computer and the hardware you run on and the architecture. And sometimes this is the only way to explain why some code performs or doesn't perform or is slower. And I find this notoriously hard. Your code runs on something like that. And that's a picture of a chip. And if you're a C++ programmer, what does that mean for you? What do you actually need to know about this thing, in practice? And if you start researching this kind of stuff, then you find, diagrams like that on the internet. This one shows a particular hardware architecture. You're going to find threads at Stack Overflow. You're going to find optimization manuals that are really hard to read. You're going to find some books about hardware, computer science. But why do C++ books never talk about this stuff? They say sometimes vague things about cache locality, being cache friendly, and obviously they talk about algorithmic complexity and this kind of stuff. But they don't really talk about hardware and what that means. And this is where my talk today fits in. I want to bridge a little bit this gap between the sort of hardware world and the C++, learning C++ world. One thing I want to say is that this is an introduction talk. So I want to give sort of like an overview over what hardware architecture can do to the performance of your code. And some of you will already know all this stuff, so sorry, maybe in this case it's going to be useful as a refresher. So my goal is really to mention some hardware-related effects and use C++ to do that. So I'm going to show a few easy C++ snippets, benchmarks demonstrating what's going on. And the goal here is really not to go into any depth with any of this, but to just make sure sort of everyone has heard about this stuff, sort of like an introduction overview. So if any of these effects actually hits you, then you recognize it, you remember it, and you know where to dig deeper. And sort of the other goal is to have a mental model about computer architecture that's easier than what's on this slide and useful for our daily C++ job. So for the rest of the talk, I'm going to do some micro benchmarks. which is basically when you benchmark a loop or a little snippet, which is sometimes good to understand things. It's also dangerous. So basically, don't do it. Don't do micro benchmarks, actually, because they're dangerous, actually. There's a thing called confirmation bias, where if you write a micro benchmark, then you will find the thing that you were looking for in the first place. Or you write a little code snippet, but then the optimizer will actually optimize away the thing that you were looking for. And you will see something completely different. So it's really easy to get micro benchmarks wrong. So don't do that. I'll be the guy who's doing that today. You should measure your real code, because this is the only way to figure out how your real code actually performs. OK, so for the micro benchmarks, I'm going to use Google Benchmark. It's an awesome library. Also, there's a lot that you can tweak. So I'm going to use basically the 3 compilers that we use in our company: Clang, GCC, and Visual Studio, the most recent versions of those. And I'm going to use, to compile those examples, I'm going to use the default settings with full optimizations on. So this is what you typically get if you just open Visual Studio or Xcode and you go to you select release mode and then you just build it and run it. And I realized that there's a lot you can do with compiler flags and additional options, and then the results will look quite different sometimes. But this is not what most people do. Most people open their IDE, they compile their code with some default settings, with optimizations, and they run that. So this is what we're going to be doing today. And also, I'm going to run these things on 2 machines. One of them is this MacBook here, which is a fairly recent one. And the other one is a little bit older MacBook with a Core 2 Duo architecture, which is just a few years older, just to show what kind of impact can it have if you use different generations of hardware. So these are desktop machines. I could also have done some stuff with ARM processors and mobile phones or maybe embedded stuff. But this is not really the point here. It's not like an in-depth study of all the different things. It's more like an overview over different effects. So this is the setup I'm going to use today. And whenever you see bars showing performance and they don't say anything about compilers or which machine it was, then you can assume that it looks pretty much similar. Right. So let's jump in. So when I started programming, for a long time, this was my mental model of how a computer works. You have memory, main memory, and then your data, like integers, are somewhere in that memory, and then you have a CPU that can access that memory. It has a certain address, so it can fetch that, and then inside it can do its computation. And then maybe it can write it back to memory. And it turns out that you can get quite far with this, but it's not quite enough. So the first time I hit a case where this was not enough was when I was a student, and I had to traverse a 2-dimensional array. I was doing some scientific computing at the time. That was like a typical thing that you would do there. So this is our first code snippet. And if you have a 2-dimensional array in C or C++, there's 2 ways you can traverse it. You can do it in row major order, or you can do it in column major order, depending on which dimension is in the inner loop. And of course, the row major version is the one that goes through memory like this, where you loop through the numbers in your array in the same way they're actually laid out in memory. So you contiguously just scan through the memory. And if you do it the other way around, then you're going to be jumping around in memory. And you're not going to scan through it, but you're going to keep jumping, which is not very optimal. And if you do this, for example, with a 10 megabyte array, which is the typical size maybe of a large image file or something, then you're going to find that if you loop the wrong way around, then in this particular example, it's going to be on this machine 30 times slower or 35 times slower than if you loop the right way around. So that's a pretty significant factor here, right? So when I first saw this, my supervisor told me, yeah, well, OK, this is one of the first things you need to learn when you do this kind of stuff. And the reason for this is that processors are really much better at going through contiguously through memory than jumping. This is just much faster. And yeah, this is true. Processors are really much better at going sequentially through the memory. This is why vector and array are a lot of the time much better than any other containers. And even though things like set or map are log n complexity with some operations, sometimes a lot of the time a sorted vector or a boost flat set will actually outperform them because it's contiguous in memory, even though the algorithmic complexity is worse. So most of the time it's really, really good to have a data structure that's laid out contiguously in memory. But this is just part of the story here. If you look at how this slowdown, if we loop the wrong way around, how the slowdown changes if we change the size of our array, then we're going to find something like this. So the x-axis here is the array size. And you see that as you get to bigger and bigger arrays, this factor of slowdown, the performance hit that you get because you loop the wrong way around, it's going to get much bigger. And if you have something like this, you can't explain this. So on the left side, with small arrays, there's like this base offset which you have because you don't scan through it contiguously with the dashed lines. So this is slower because of things like, for example, if you don't access it contiguously, then the optimizer can't vectorize it and things like that. So this is like a base price that you pay because you access your data the wrong way around. But then as it gets bigger, there's something else going on there. And of course, as I'm sure many of you, or most of you know, this is because we have to revise our mental model here. This is not enough. Between the memory and the CPU, we have a cache. And a cache is much faster than a memory, but it's also smaller. And if you have a big array, then the structure doesn't fit into the cache. And if we keep jumping around in it, we're going to access different parts of the array that are not in the cache, and we're going to get cache misses. So we're going to have to fetch these parts from main memory, which is much slower. And the bigger the array is, the more of these cache misses we have. And that's the reason why the dashed curve so the difference, the distance between those two curves gets bigger as the array gets bigger. And if you look closer, we see that this performance hit that we are suffering here comes in discrete steps. So we have certain places there where all of a sudden the performance jumps and gets worse. And this is because cache is hierarchical, right? So in a modern computer, we have typically something like 3 levels of cache, where basically every level here is an order of magnitude bigger and an order of magnitude slower. So we have these different levels. And as your array gets bigger, you get one performance hit as soon as your array doesn't fit into the level 1 cache. And then if it gets bigger, you suffer another performance hit once it doesn't fit into the level 2 cache anymore. And then you get level 2 cache misses, which are even more expensive, and so on and so forth. And the slowdown I'm talking here about is latency. It's not throughput, like how much data you can move between those levels, but it's how expensive it is initially if you say, hey, I need a number now, which is not in the cache, fetch it. How long does this initial access take, the latency of that? And that's the thing that's expensive. Right. So let's go back to the 2D array example. This is a very silly code example because we just loop through the array and then we do one addition to every element. This is not really how real code does. So let's change this code a little bit and add a little bit of number crunching to it. So here I just added a few silly operations. We do a multiplication and an addition, and then we compute a hash, and then we compute a square root. This is not really meaningful, but this way I can just keep the CPU busy doing some number crunching and sort of simulating what's going to happen in real code when you also need to compute some mathematical operations. And then we just do the same benchmark again. And then we see that it looks different. And actually, so again, the array size is the x-axis. And then we see that for a lot of the range here, actually, the way we loop through the array, whether we loop the right way around or the wrong way around, it actually doesn't really matter. And only if the array gets over a certain critical size, then we again have this performance hit because we don't access the memory in the right way. And I think this is interesting. We can really like sort of draw this kind of line here and say, well, okay, so to the left of that line, the runtime of our code is really determined by the computation that we do. So this like hash and square root stuff that you saw. So this is going to determine how fast our code is going to run. And to the right of that blue line, actually how fast our code is going to run is determined by the data access. And there, actually, it's slower because we don't access our data in the wrong way, in the right way. And this becomes even more obvious if we now overlay this with the previous benchmark, where we just loop through the array and we don't really do anything with it, which is the black line. And if we draw this line here again, then we see that to the left side, again, how fast our code is determined by what we compute. So in the black case, it's just one addition, so it's much faster. Whereas for the red line, we do all this like square root and hash stuff, so it's going to be more expensive, so it's going to be much slower. But then, if you look to the right side of that, at the dashed line, where we loop through the array the wrong way around, actually the code that does all the hash and square root computation and the code that just does nothing, except accessing the data, they run with the same speed. So actually, it doesn't even matter at all there how much stuff you compute, because the runtime of your application is entirely determined by accessing the data and the way you access the data. And that's the limiting factor there. So we're bound by data access. And in a real-time application, you really don't want to be on the right side of that blue line. You don't want to be bound by accessing your data. You want to be bound by your computation, because you can optimize that. You can find a better algorithm for that. So it's really, the ideal point is sort of here the sweet spot where sort of like computation and data access are both, sort of like none of them is like dominant over the other. You're in the sweet spot where you can sort of optimize it well. And it's going to actually improve your performance. So if you're on the right side of that line, that's typically really bad. And the worst thing about this is that it's really hard to find that out, right? So if you have a performance problem, what a lot of people do is they do profiling. And most of the time, people do something like time profiling, where you have a tool that tells you how much time you spend on a function. So if you do this here, so this is what Xcode gives you. If you do Xcode Instruments on Visual Studio, this will look very similar. And this tells you, well, unsurprisingly, you spent 100% of the time in main. And then 13% of the time you spend in this templated stuff there, which is essentially the square root. And then, OK, so probably the compiler did inline the hash. So probably the rest of the other 87% are probably spent in the hash computation. That's something that you could now think. So you would go off and optimize your hash function, and 1 week later you would come back with a better hash function that's 2 times faster, and you plug that in, and you find out that your code runs just as slow as it did before, because you're not bound by your computation. You're bound by the way you access your data. And this doesn't tell you at all. I mean, Xcode has a thing, and probably Visual Studio somewhere as well, where it's quite hidden away, but it tells you cache misses. Like, it tells you, OK, you have 1 million cache misses per second. Is that a lot? I don't know. So it's really difficult to find this stuff. And then your IDE doesn't quite cut that anymore. So in order to figure out that here, actually, the problem is not what you compute, but your data access. You're waiting for data all the time, and that's what you're slowing you down. So to find that out, you need specialized tools, like Perf, for example, is a good tool. VTune, I think, can do the same thing, where it actually can tell you how much time do you spend in an instruction, on an instruction level. And then you see, oh, actually, most of the time you're waiting for data. So data access, the way you access data here is important. And if you want to do a traversal through a 2D array, just like we did, then maybe you want to access, the best way to do this is to access the memory like that, where you scan contiguously through it. If you have another problem, like maybe you're editing images, and then maybe you have like a 2D image, and then you want to like paint a blob somewhere in a region of that image. And maybe in this case, the best data layout for this would be something like that, where you have like tiles, and then that's the way you lay out memory for this problem. And the size of a tile probably will depend on the region that you're editing, and maybe on your hardware as well. Or maybe for another problem, this would be a better way to lay out your data. It doesn't really even have to be the best data structure. It just has to be good enough so you're not bound by waiting for the data. So data that you're accessing needs to be close together. So this is really a silly example, but if you have a class of foo and a bar, and for some reason you always access, you have a vector of foos and a vector of bars, and for some reason you always access a foo and a bar at the same time, like at the bottom there, then probably it's better to just stick that foo and a bar together in a struct so that they're next to each other, and probably that's going to be better. So what you want is cache locality. And this holds in space, and this also holds in time. So if time goes on, and then you access the green piece of data, and then the red piece of data, and then the blue piece of data, and then the green piece of data again, maybe by the time you do that, it's not in the cache anymore. So you have a cache miss, and you have to fetch that. It might have been evicted from the cache. So it's really better to do it like that, where you generate the green data and you use it immediately, and then you go on and do something with other pieces of data, instead of letting the green data hang in the cache and hope it's going to be there later, because maybe it won't. So that's temporal cache coherency, which is another thing to look out for. Let's look at something else here. So what we're doing here is we're missing one piece about the cache here. Here we have an array, and now we're going to access every nth array element. So either we're going to access every element, or we're going to access every second element, or every fourth element, or every 100th element. And we expect basically that the less data we have to touch, the faster it will be, right? If you only have to access every 100th element, it's much less data that we have to touch, so it's going to be faster. And if you measure that, if you vary the step size here, and you measure that, then it's going to look something like that, where you see, if you touch every 100th element, it's going to be faster than touching every 10th element. So it goes down linearly, just like we would expect, but only up to here. And then if you access every 16th int, this is an area of ints here, if you touch every 16th int on this machine here, it's just as fast as if you touch every single int. So you touch 16 times more data if you touch every single int, but it's going to run just as fast if you touch every 16th int. And the reason for that is that cache works in cache lines. So on a typical desktop machine, a cache line is 64 bytes, which means it's 16 ints. And so data, if you fetch data from the cache, it comes in cache lines, which means that you can only get a whole cache line. And if you access one int in the cache line, then you get the whole cache line, and then the other 15 ints that are in that cache line, you get them for free because it's already in the cache. So it's useful here to think in these cache lines. So touching a cache line once, basically, and then you already have all the data that's on that cache line. One more thing about traversing data. So we saw that if you have a 2D array, then that's a good way to access the data structure. And if you loop the wrong way around, then it's bad. A lot of the time, you don't have something like this, but you have something like that. For example, if you have a list or a map, so then the data will be at random spots in the memory, and then you're going to keep jumping like that. And there was a talk last year about different STL containers from Klaus Igelberger called Taming the Performance Beast, where he was benchmarking all these different STL containers and how they behave. Great talk, can really recommend you to watch it. I'm not going to go into STL containers here. The only thing I want to say here is that this kind of like randomly jumping actually So first of all, you can avoid this by, if you have a list, for example, and if you keep inserting and deleting, then you end up with something like that. But then instead of doing that, you can actually reuse the nodes, and you can use a custom allocator and things like that, where you can avoid the list ending up like that. But if you have a data structure like that, and you run it, then this is another benchmark. I'm not showing the code here. You're going to find out that actually, if you do it with the 2D array, then going through the data in a random way is actually even worse than going through the data in this wrong column major way. So this kind of random access is basically the worst thing you can end up with. And why is jumping randomly worse than jumping the wrong way, but like with a constant stride, which is if you do column major order in a 2D array? And the reason for that is that if you look at modern hardware, then it has a thing called a prefetcher, which sits between the CPU and the cache. And whenever you access data, with a regular stride, it recognizes this regular pattern, and then it latches onto it and starts prefetching the data. It starts guessing, oh, well, if you touch every 16th data element or whatever, then maybe this is the next one. So it's prefetching it from the cache, and that's going to be faster. But if you have a random data structure, then this is not going to work. So you're going to suffer an additional performance hit there. Right. One last effect that can happen with the cache. So here we again access every nth array element, but then the way we did it here is we're always going to access 10,000 elements. And then it's going to be, so either we're going to touch every 16th element, or maybe every 32nd, and so on. And we're going to increase the stride, but we're always going to touch 10,000 ints. And we're going to start with 16, so they're all on different cache lines. So we're going to touch 10,000 different cache lines, right? And you would expect that if you do that, it's always going to take the same time, right? Because we just touch 10,000 cache lines every time. And if you do that, we see this, which I think is really, really interesting. So yeah, if you touch every cache line, and then if you increase the step size, it takes the same time until you get to a step size which is 256. And then all of a sudden, performance drops by a factor of 20. And then if you keep increasing the size, it goes down again until you get to 512 as the step size. And then it again is 20 times slower. So this is really weird, right? Somehow, if you have powers of 2, this seems to be a very bad size for your step. And this is, I think, a bit counterintuitive, because we all assume that computers are really good at powers of 2, right? So why is this going to happen? Anyone knows? Can you shout? Yes, associative. It's cache associativity. That's the reason here. Let me try to explain this in 1 minute. Let me see if I can do this. So cache associativity, what is it? Imagine all your bytes in memory are cars. And you have 100,000 cars, 100,000 bytes. That's your memory. And then every byte has an address, and that's like the license plate of the car. And then you have a parking lot with 10 spaces, and that's your cache. Now, you can put these cars into the parking lots. And there's 2 different ways to do this. There's one thing that we call fully associative cache, where any car can go to any parking lot, which is really good, because then you can use your cache in the optimal way. But the problem with this is that it's harder to build in hardware. It's going to be slower, because if you can route any car to any place on the parking lot, you're going to end up with more complex logic in the hardware. The other way to build a cache is a direct map cache, where you can say, OK, every license plate that ends on 2 can only go to slot number 2. Every license plate that ends with the number 3 can only go to the parking lot number 3. And this is much easier to build in hardware, because the routing to the right slot in the cache is going to be easier. So they're going to consume less energy, they're going to be faster, they're going to be easier to build, but they're also limited. So most modern computers do a compromise, which is called a n-way set associative cache, where you divide the cache in sets, and then every set itself is associative. And here's a typical, here are some typical numbers, like for example, on a machine like this, you can have, if you look at level 2 cache, you can have a 128 kilobyte cache. It can be 8-way associative, which means you have 8 sets, and each set is 16 kilobytes. Now, let's say we have 20 ints, just 20 integers. But then they're 16 kilobytes apart. It means that every integer can go only into one slot in every set. So in every set, there's only one slot any of those integers can go. And if you then keep looping through these 20 ints, there's only 8 slots for 20 ints, and they're going to keep evicting each other out of the cache all the time, and you're going to get cache misses with every single one of them. So that's the reason this is so slow. So this is an interesting effect that you could keep in mind. So one last thing about the cache is there's a data cache, there's also an instruction cache, where your code that goes that is being executed. And the instruction cache, performance problems with the instruction cache are not much of an issue in practice. Code that's bad to the instruction cache is basically code that jumps and branches a lot. We're going to talk about branches later. Let's look at the memory first. So, memory basically, yeah, it's a big chunk of memory. It has different addresses, and you could think that, well, yeah, okay, you have memory, and then you have different data structures that have different data types that have different sizes, and they can go to different locations in the memory, and they're going to have an address, and that's it. It turns out actually that this is not the way memory works. Memory doesn't look like that. Memory looks much more like this, where every type has an alignment requirement, and for example, an int will be aligned to 4 bytes, and then you will have a word size, which on a 32-bit machine will be 4 bytes, on a 64-bit machine will be 8 bytes. In C++, you can query the alignment of every data type with align-off. That's a keyword for that. And actually, this is the way data is laid out in memory. And if you have this, then you get the funny effect that so basically this is how if you declare a struct, this is how the compiler will lay out your data structure. And then you have funny effects like the size of your struct may depend on the order in which you declare your variables, just because everyone will be aligned. So if you have a double, which is 8 bytes, it's going to be aligned with 8 bytes. So if you change the order sometimes, the size of your struct is going to be different, because they're going to fit differently into these alignments. Now, Clang has a thing, for example, fdump memory layout, where it can show you the memory layout of your class. And if you write portable C++ code, you're always going to get this. Sometimes you don't want that. You want to have a structure which is not aligned. And this, there are platform-specific compiler intrinsics for this. For example, in Clang, you can achieve this with attribute packed. In Visual Studio, it's called pragma pack. So you can force the compiler to have a structure that's not aligned in memory. And at that point, it depends on the hardware what's going to happen. Some hardware can handle this, some hardware cannot. On some machines, you're going to have something like, if you want to access this double here, which are these 8 red bytes, if you want to access it and it's not aligned, then what the computer will have to do for you is it's going to have to fetch 8 aligned bytes and the 8 aligned bytes after it, and then it's going to have to shift them around and combine them to get your double there. And on some machines, this is what's going to happen. Some other machines, they do have a means to access unaligned data directly. On some machines, like on an Android phone, for example, if you try to do unaligned memory access, a lot of the time it will simply crash because the hardware doesn't support that. So this highly depends on your hardware architecture. This is, for example, one reason why reinterpret cast is undefined behavior. I struggled a long time to understand this. Why can't we just take these 8 bytes and say, OK, let's interpret this as a double? This is what computers do, right? Why is this defined as undefined behavior? And one of the reasons is that, well, it might not be aligned correctly with the other type that you want to use, and your hardware may be unable to do that. So that's one reason why reinterpret cast is undefined behavior. The other one is aliasing. But yeah, we can do this unaligned memory access, and if you do that, okay, I'm going to skip over the code, but I did a benchmark, and then you find that, for example, on this machine, so the black bar is aligned and the red bar is unaligned. Actually, this machine doesn't have a problem at all with unaligned memory access. Actually, it's a little bit faster because if the data is packed and the structure is a little bit smaller. So maybe I can just use this packed thing everywhere, and it's going to speed up my code. And on the other MacBook, on the slightly older MacBook, if you have unaligned memory access, it's 3 times slower, right? So there, the hardware can't handle unaligned memory access that well. And it's actually the same binary running on 2 different Macs. And in one case, the unaligned version is 3 times slower. So yeah, hardware really matters here. So we come back to alignment a bit later. It's a little bit of a dry topic, so let me do something a bit more fun. OK, let's look at this example here. So I have a vector of floats, and I'm going to fill it with randomly with 1 or -1. So the vector is going to look like -1, 1, 1, -1, -1, 1, 1, -1, randomly. And then the next thing I'm going to do is I'm going to count how many +1s I have in there. So roughly half of them will be +1s, right? Now, before I do the count, I can also sort the array. So all the -1s comes first, and all the +1s come afterwards. And obviously, this is not going to change how many plus or -1s there are. It's not going to change the result. It's not even going to change anything in the count if. It's going to do the exact same thing. But if I sort it, maybe this influences how fast this code runs. Who thinks that if I sort it, it's going to make a difference? Right. What do you think is going to happen? The count will be faster. By how much? Can you guess? OK. So I benchmarked this, and it depends on the compiler. In Clang, it doesn't make a difference. In GCC, it doesn't make a difference either. If you do it with Visual Studio, the version that's not sorted is going to run 6 times slower. Although it's the exact same instructions that you're executing there. What's going on here? What is it about this thing that makes it run 6 times slower if the plus and -1s are sorted? And at this point, if you want to understand this, and you have different compilers doing different things, you need to really look at what kind of assembly it generates. So I did that. And if you look at the Microsoft Visual Studio version, so it's comparing the numbers whether it's bigger than 0, so that's the commiss instruction. And then depending on that, it's either going to increase the counter, that's the inc AC there, or it's going to jump over it, so it's going to not increase the counter. So there's a jump in there depending on the result of the comparison. If you look at the GCC thing, it's also comparing the number with 0, but then depending on the result, it's going to do a conditional move. Yeah, so there's no jump. It's going to do the conditional move, and it's going to keep going. So there's no branch there. And if you look at the Clang, what Clang generates, then it's some SIMD stuff. There's not even a counter in there. So this does what you expect. I think if you would stare at it long enough, you would understand how this works. I didn't have the patience to do that, but it works. Yeah. So Clang generates some really, really clever vectorized code there. So the Microsoft compiler generates this, it's the only one that has a jump in there. And why is this 6 times slower if the data is randomized? Well, the reason for that is because of the way the CPU and the pipeline works, right? So if you, if you Google, if you look at the Wikipedia article for a CPU pipeline, this is what you're going to see, where every square in there is an instruction, and then there's a pipeline and executes them in several steps. Actually, in practice, it's not as simple. You don't have 4 stages. You have on a modern Intel CPU, it's more like something like 20 stages. And also, the instructions in the CPU, they're further decomposed into micro instructions. It's really, really complicated. But this simplified version, something like this. And if the blue one is the comparison, then basically if you have a jump, then the red one will be different instruction depending on whether the blue one, the comparison was true or false. But this obviously can't work here because by the time we evaluate the blue instruction, the red is already in the pipeline, it's already executing. So you need to, and if you don't know which instruction this is going to be, because you have to evaluate the blue one first, then this is what's called a branch hazard, which means that you have to either wait, so the CPU has to wait, and until the result of the blue instruction becomes available before it can do the red one. So this is going to slow down your code. To avoid that, modern CPUs have a thing called a branch predictor, yeah, which it's going to guess what the outcome of the comparison will be and speculatively execute the next instruction. So it's going to guess what the next instruction will be. This is really complicated technology, but it works really, really well on modern CPUs. And it's working especially well with branches like this, where you have a loop terminate condition, which is going to be false most of the time, except the last time around. Or you have a comparison, like a check maybe, that's going to be false most of the time, except sometimes. And in this case, the branch predictor can guess what the outcome will be of your branch, and most of the time it will be correct. So you're not going to suffer this performance hit. And these days they're really good. They can also spot like patterns. But what these branch predictors can't deal with is true randomness, right? So if it's really random what the outcome of the branch will be, then the best branch predictor in the world cannot guess what the outcome will be. So this is what's going on here. You're suffering. So the reason we have this 6 times slowdown is because we suffer the impact of the branch predictor. Another example where you can have branches is with virtual function calls. So this is a really silly example where I have polymorphic classes and I have a virtual function which returns, depending on the actual class that I'm using, it returns a different number. And what I'm going to do is I have a vector with these polymorphic objects, and I'm going to, so mammal, dog, and cat will return different numbers, right, if you call this function. So I'm going to put 10,000 mammals in there, 10,000 dogs, and 10,000 cats. And then I'm going to just call this function in a loop and sum up all the numbers. And then sometimes what I can also do is, before I do that, I can shuffle them, right? Or I can not shuffle them. So this is analogous to the previous example, where instead of is it bigger than 0, I have like which is the actual function, the actual virtual function that I'm going to execute. And if you do this, you also suffer this branch predictor hit here, which is the black bars, except that now the compiler can't optimize this away, right? A virtual function call is a branch that the compiler is not going to be able to optimize. And people claim sometimes that virtual functions and vtables are bad for performance. Well, 99% of the time, this is not going to be the case. But if it's going to be the case, there's a high chance it's not actually the additional indirection and the offset of the vtable, but it's actually the branch that you're introducing there. That's going to be your problem. A curious detail here is also that Clang is this time slower than the Microsoft compiler. I guess this has something to do with how they implement vtables. But I haven't looked into this, but maybe I should. I think this is interesting. So another example here, another thing I want to quickly mention is, let's say we have an integer a, and then we have a silly function that's just going to do something to this a. It's going to like increase it, increment this in a loop, and then we're going to do this from different threads. So we have like 4 threads, and they're all going to access the same variable. Actually, of course, this is not valid C++ code, because if you write to the same memory location from different threads, that's a data race. That's undefined behavior, so let's not do that. So let's just, for the purpose of this benchmark, get around it by making it atomic. So what we do here is we basically increment a counter simultaneously from different threads. And if you do this, we find that we suffer a massive performance hit. If you have like 4 threads accessing the same int, then it's going to be much slower actually than if you just execute the different things sequentially, right? So instead of a speed up, you have a slowdown. And the reason for this is, if you have cache and you have different cores, then some of the lower cache levels will be per core. But then if you have one variable that different threads are accessing, it's going to be present in all of these levels. And then if one core writes to it, it's going to dump it to the cache that's common to all the cores. And then if another core has a copy of that variable, it's going to invalidate that copy. So the next time the core 2 is going to access A, it's going to have a cache miss there, and it's going to have to fetch it from the next cache level, and that's going to be much slower. Now, this is the reason why it's much slower to access the same, why the previous example is much slower. But what you can also do is, in this example, which is something that we call false sharing, where here I have different variables, A, B, C, and D. So there's no data at all shared between the cores. Yeah? Every core accesses its own variable. But then if you benchmark this, you get the same result, that you have a massive slowdown. And why is this the case? Well, if you remember that memory is aligned, and if you imagine these cache lines, and then one cache line is maybe one of those bookshelves, and then memory are like a lot of those bookshelves, and here's a cache line. Well, it's also aligned. A cache line is aligned with the size of the cache line. And if your cache line is 64 bytes, then that means that all the addresses which are something something 00 to something something 3f, they're going to be on the same cache line. So in this example, A, B, C, and D, although they're different variables, they're all in the same cache line. And this thing, well, that works in cache lines, right? So, which means that if you have different variables, but they're on the same cache line, and you have multiple cores, you're going to suffer the same performance hit as if it were the same data. And you can prevent that, for example, by aligning your data with the cache line size, which forces the pieces of data to be on different cache lines, so you don't have this problem anymore. And if you do this, then you get the red bars where you don't have that slowdown anymore. Right. Let's look at this example here. Let's go back again to the CPU pipeline. So we were talking about branch hazards. One more type of hazard that I want to mention today is the data hazard, which is basically if you have, again, the blue instruction and the red instruction that you're going to execute next, and then the input data for the red instruction depends on the result on the blue instruction. So this happens, for example, let me skip this. Yeah. So this is a really simple example for this. So this is a silly loop. It doesn't really mean anything. But the point here is, so we have these different arrays, and then we're going to loop through them and do some stuff to them. So this is what the loop actually does. Yeah. So you see that what happens here is that if you use this bi plus 1 in the second line, and then in the next loop iteration, you're going to access the same data. So that's the problem that you have here. If you compute the result and then you use that result in the next instruction, then you're going to have this problem that if these are instructions that one after the other in the pipeline, then again you have this problem that you can't execute that instruction until you have the result, so you have to wait. And a lot of the time, computers get around this without you even noticing, because the optimizer is reordering your instructions, right? So to get around this. And then by the time your compiled binary gets to the CPU is again going to reorder the instructions. So a lot of the time, you're not going to have this problem. But sometimes if you have just 2 lines of code and they're run in a hot loop, and you always need the result of one computation in the next computation, you're going to have this problem that you can't execute the next instruction because you need the result of the previous one. So the pipeline has to wait, and you're going to suffer a performance hit. So sometimes then what you can do is you can rewrite your code in such a way that you don't have this data dependency. Sometimes it's simpler than this. In this case, if you would execute the same loop, there is a way to make this run faster. Anyone has a suggestion? Yes? Skip the first iteration and assign C minus 1. Sorry, say again?
A0 and B0 fill with correct value, and when they move, add only C minus 1.
Okay. It might be equivalent. What you said might be equivalent to what I'm going to do now. So what you can do here is you can write it like that, where basically the only thing you do is you shift your loop so that you do the first instruction first, and then basically instead of the loop being the first and the second line, and then the third and the fourth line, it's going to be the second and the third, and the fourth and the fifth. And does everyone see that the right hand side is the exact same thing as the left-hand side? It's the exact same thing. Except for one difference. What did we do here? Why is the right-hand side better? Yeah. It still has a problem. Okay, let's talk about this afterwards. Yes, exactly. It still has the dependency. It still has the exact same dependency. So we didn't actually do anything, right? But if I run the right-hand side, then it turns out that it's actually much faster. I'm going to show the result in a second. Why is the right-hand side much faster, although it's the exact same code? Well, exactly. What we did here is that we still have the same dependency, but by shifting this loop, the different iterations of the loop don't depend on each other anymore. So one iteration of the loop does not depend on the previous iteration of the loop. And if you have something like this, what can the optimizer do with that? Sorry? Loop unrolling is something else that it also does, but it's not going to do very much in this case. But it can vectorize it, right? It can vectorize it. It can insert instructions which perform the addition on several pieces of data at once. So this is called SIMD. We have another talk. We have a talk about SIMD this afternoon in track D. But yeah, basically it's another property of hardware that you have these SIMD instructions where you can do an addition or other operations on 4 integers or 8 integers at once, depending on what kind of SIMD you have in your machine, like SSE or AVX. And yeah, so if you do this, you see that the right-hand side is actually 3 times faster than the left-hand side, which is sort of typically the speed up that you get with SIMD instructions. And if you look at the disassembly of that code, you see that, yep, so that's clang here. The left-hand side doesn't have any SIMD instructions. The right-hand side has these SIMD instructions which work on 4 integers at a time, so it's much faster. And surprisingly, none of the compilers that I've tested did this optimization of shifting the loop automatically. So in this case, you have to do it by hand. And then it speeds up your code by a factor of 3. So one quick thing I want to mention about the SIMD stuff is that, again, alignment matters. So if you have SSE, for example, then an SSE register is 4 ints, like 6 or 4 floats, 16 bytes, or maybe if you have AVX, it's 32 bytes. But then this is also aligned with the SSE register size, right? So here's an example, which is actually something typical for audio algorithms, the kind of stuff that I do. So here you have 2 arrays with floats, B1 and B2. And what you want to do here is you want to do multiply add. So you want to loop through both of them and multiply buffer 2 with the number and then add it to buffer 1. And then do that in a loop. And then this is something that every modern compiler will vectorize this and will insert some SSE instructions to make this faster. But this sort of like works really well if both of these pointers that you pass, buffer 1 and buffer 2, are aligned with the size of your SSE register size, something like 16 bytes. And if we try to call this multiply add and we offset those pointers, so we offset them, one of them by 1 int and the other by 2 ints. So it's not unaligned memory. It's still okay for the int, but it's not aligned with the 16-byte SSE register size anymore. And if you do that, we see that we suffer a performance hit again. This is the red bar. And on this machine, it's going to be something like 15% slower if you don't align your data with this 16-byte boundary, which is very significant. But if you do this on the slightly older MacBook with the other architecture, then actually unaligned, not aligning your data with the SSE register size is going to slow it down by a factor of 3, which completely destroys the performance gain that you have from SSE in the first place. Right, so that's another thing to consider. Do I have like a couple more minutes? Let me mention my very, very last example. And this one is fun. We take a floating point number, x, and we're going to do 10,000 multiplications on it. And we multiply it with a number that's not going to really change the value of the floating point very much. So it's like 0.999. So it's not going to change the value by very much. And we do 10,000 multiplications in a loop. And we do this with different values for x. We do it with 1. We do it with 1 divided by 0, which is what? It's inf. We do it with 0 divided by 0, which is what? That's non, right? We do it with minus 0, which is something else than plus 0. We do it with a very small floating point number, and we do it with a very big floating point number. Otherwise, it's all the same. Is any one of those values going to give us a performance problem? The small number. Why? Denormalized, exactly. It's a denormal. By how much slower will it be? What do you think? 10 times. Not bad, the guess. It's almost 30 times slower, right? The small number is the denormal, which in IEEE floats, if you have the sign, the exponent, the fraction, the normals are the ones which are really, really the smallest numbers that are bigger than 0, where the exponent is 0, but the fraction is non-zero. And then you have this other way of interpreting the floating point numbers, where usually the fraction is understood in a way that you have an implicit 1 dot before it, but then for the normals that's not the case. To be able to represent these small numbers. Modern hardware is really struggling with those numbers. And if you know this kind of stuff, then there are ways around it. So depending on your platform, there's flags and there's things in your code, compiler intrinsic calls that you can make to flush the normals to 0 or to treat them as 0 to get around this problem. But obviously, in order to get around of this problem, you need to be aware of the problem. And I've actually seen at least 2 times in practice where an algorithm an audio algorithm was producing the normals, and that was really hitting performance in a measurable way. So this is another thing to be aware of. Okay, so this was the last example that I had. This was the stuff that we talked about. Here's a summary slide. Well, if you want fast C++, you should be nice to your hardware. So these are the different things that we discussed. I'm at the end of my talk. Thank you.